Welcome to yet another lecture. In this lecture, we are going to talk about the topic measurement. This is quite a long topic, so it is split into several subtopics, including physical quantities and units, measurement of length, measurement of area, volume, mass, density, and measurement of relative density. So let's go straight to the first subtopic, which is physical quantities and units. And we want to start by looking at some of the objectives in this lesson. So by the end of this lesson, I will expect you to be able to define the term physical quantity, list examples of physical quantities, distinguish between basic physical quantities and derived physical quantities, and finally, list the 7 basic physical quantities and their units. So let's start by the definition of physical quantity. What is a physical quantity? Now, the term physical quantity is used in physics to mean those features of an item which can be measured. We usually measure physical quantities using an instrument. For instance, you can use a ruler to measure length. So length of, let's say, a table is a physical quantity because you can use an instrument to find its size or to measure it. So as a definition, the term physical quantity is used to represent those features of an item that can be measured. So the equation which is associated with this definition is physical quantity is equals to number plus unit. For instance, we can talk about mass of a book being 800 grams. Mass is the physical quantity. Book is the item. 800 grams is the magnitude of that physical quantity. So you can see the rule has been obeyed here. When you talk about the size of a given physical quantity, you must give it a number and a unit. That is the first rule in physics. So mass of a book is equal to 800 grams. Mass is the physical quantity, book is the item, and of course 800 grams is the magnitude or the size. And it is represented by a number and a unit. Now, I want you to take a moment, pause the video, and list at least one feature of each of the following items that can be measured or that is measurable. Okay, welcome back. Let's look at the car. You can talk about mass of a car being equal to 1500 kilograms. Mass is the physical quantity, the item is the car, 1500 is a number, kg is a unit, and 1500 kg is the magnitude of that physical quantity. It is the magnitude of the mass. We can also talk about speed of the car being 80 kilometers per hour, for instance. Momentum of the car could be given as 30,000 Newton seconds. In all these measurements, notice that the item remains the same. It is the car, but there are various features of the car that can be measured. These include mass, speed, momentum, and many others. Let's look at the child. We can talk about mass of the child being 40 kilograms, the weight of the child being 400 newtons, and of course maybe the height of the child is 1.2 meters. Again, the same rules follow. Finally, we've got water. We can talk about mass of water being 5 kilograms, density of water 1000 kilograms per meters cubed, volume of water 30 centimeters cubed, and of course temperature of the water being 56 degrees Celsius. So we have already observed that a given item could have more than one feature which can be measured. So when we talk about water, we can measure its mass, that is one feature. We can measure its density, that is another feature, volume, temperature, and so forth. In other words, a given item can have more than one measurable feature or it can have more than one physical quantity. These examples illustrate the fact that physical quantity is the term which is used to describe measurable features of an item. And therefore, mass, density, volume, temperature are all physical quantities. Now, of these physical quantities, we have basic and derived physical quantities. What is the distinction between basic and derived physical quantities? So let's look at the distinction between a basic physical quantity and a derived physical quantity. Now, a basic physical quantity is that quantity which cannot be obtained from any other physical quantity. Now, each physical quantity has an SI unit. There are 7 basic physical quantities, and this means there are 7 SI base units or SI units. So let's start by looking at these 7 basic physical quantities, the SI unit of each one of them, and the symbol used for the SI unit. And you're going to start with length. Length is a basic physical quantity. Its SI unit is meter, and the symbol for meter is lowercase m. The next one is mass. The SI unit of mass is kilograms, and of course, the short form or the abbreviation of this SI unit is kilogram. Notice that I'm talking about the symbol for the SI unit. It is not the symbol for the physical quantity. The third physical quantity is time. The SI unit of time is second, and the symbol for the SI unit for time, which is second, is S. Again, lowercase s. Let's look at electric current. There is some difference here. The SI unit of current is ampere, and the symbol for ampere is uppercase A. You can see that one here, uppercase A. This is important because ampere is the name of a person, a scientist. And when units are named after a scientist or a person, when it is written in full, that word or that unit will start with lowercase. But when it is written in short form, it will start with uppercase. That one is a very important rule for you to be able to observe in physics. Thermodynamic temperature is another example. The SI unit of thermodynamic temperature is Kelvin, and the short form of Kelvin is uppercase K. Then we've got amount of substance, which is the mole. The short form of mole is MOL, pronounced as mole. And the last of the 7 basic physical quantity is luminous intensity. The SI unit is candela, and the short form of candela is CD. Now, this is a very important table. I would recommend that you recall these 7 basic physical quantities, because all the other derived physical quantities will be based on these 7 basic physical quantities. Very, very important. And as you recall this, I would like you to observe how each SI unit is abbreviated. Where uppercase letter is used, please stick to that. Where lowercase is used, stick to that too. And I'd like to draw your attention to the SI unit of time, which is second. You'll find that even in some textbook, they write SEC as the short form of seconds. That is not true. The short form of second is just S. When it comes to ampere, you'll find that sometimes they abbreviate it as AMP, amp. That again is not true. Strictly speaking, the short form of ampere is uppercase A. Now let's turn our attention to derived physical quantities. Now we have just seen that a basic physical quantity is a quantity which cannot be obtained from any other quantity. And there are 7 of them. And we have agreed that it is important that you recall each one of those 7 basic physical quantities. Now, what is a derived physical quantity? Like you have guessed, a derived physical quantity is a quantity which is obtained from other quantities by either multiplication or division of other physical quantities. We shall see this in a moment. Now, each derived physical quantity has an SI unit, unless it is a ratio of 2 physical quantities which have got the same unit. There are, of course, very many derived physical quantities. And physics consists of these derived physical quantities. There are very, very many. So here we are just going to look at a few examples. Now, we are going to look at the derived physical quantity and the symbol for the SI unit. And the first one is area. The SI unit is meters squared, followed by volume. Its SI unit is meters cubed. We are going to see how we obtain this SI unit. The density is measured in kilograms per meters cubed. Force is newtons or kilograms meter per second squared. Pressure is newtons per meters squared. Work is joules or kilograms meters squared per second squared. Let us see how we obtain these derived physical quantities. And I'm going to start with area. Suppose you are given a shape like this. Area is a measure of surface. So this surface has got a length, let's say, of 2 meters and a width of 1.5 meters. You will obviously agree with me that the area or the measure of this surface is given by length times width. The length is 2 meters. The width is 1.5 meters. When you multiply 2 by 1.5, you get 3. When you multiply meter by meter, you get meters squared. Therefore, area of this shape here is equal to 3 meters squared. Notice that I'm following that rule, which states that physical quantity is equal to number plus unit. And when I name a physical quantity, I want to talk about area of something, not just area. Just like when we were talking about the car, we talk about the speed of the car, not just speed. So over here, I'm talking about the area of this shape here is 3 meters squared. Area is the physical quantity, this time derived physical quantity. This shape is the item, and of course I've got a number and a unit. I'd like you to stick to these rules. It's very important in physics to observe that particular rule. Now what I want to alert you here is area is derived from length and another length. It is obtained by multiplying one physical quantity and another one. So you can see again, when we defined a derived physical quantity as a quantity which is obtained by either multiplication or division, you can see here area is obtained by multiplying 2 lengths. Let's look at the volume. Suppose this shape was a cuboid and it looked like this. This is the length, width. Let's assume the height was let's say 3 meters. Let's just assume that. So the volume of that shape will be the length times width times height. Of course, length times width gives us area. And of course, times the height. When you put these numbers down, we are going to get 3 meters squared times a height of 3 meters. And we are going to get 9 cubic meters or 9 meters cubed. Again, you see how the units have been obtained. They have been obtained by multiplying meter by another meter 3 times, and we get meters cubed. Let's see how physical quantity volume has been obtained. It has been obtained by multiplying these 3 lengths together. How about a physical quantity such as, let's look at force, for example. No, I think pressure is the best example. Pressure is defined by this equation, force divided by area. We shall look at that definition in our next topic, so don't worry about it right now. So you can see pressure is derived by dividing one physical quantity by another one. Again, the rule. A derived physical quantity is that which is obtained by either multiplication or division of other physical quantities. This time, we are dividing force by area to get pressure. So pressure is a derived physical quantity. How about the units? The unit of pressure, written by putting P in this square bracket, is equals to the unit of force, which is the newtons, divided by the unit of area, which is meters squared. And that is where I get newtons per meter squared, or newtons divided by meters squared. And you can see that since pressure is a derived physical quantity, the newton per meter squared is also a derived unit. As we go along, I'll be able to explain how this unit can also be written like this. Pascal, or the Newton is written as kilograms meter per second squared elsewhere within this particular course. So don't worry when you see this. In this particular lesson, I just wanted you to understand one thing, that we've got a derived physical quantity, and therefore the unit for that derived physical quantity is also derived. And we can be able to derive the unit of a derived physical quantity if we know the equation that is associated with the definition of that physical quantity. What does that mean? Pressure is defined as force exerted normally per unit area. The equation associated with that definition is this one here. The moment I know the equation, I'm able to derive the unit of that physical quantity. So let's stop this lesson at this point, and in our next lesson we are going to look at the second subtopic.